All right, are we ready to get started? Let's have some fun today. It'll be fun. Are there questions from last time about all of the functional programming bits that we went through? We talked about the three different ways to do the word count with the letter A, and it was fun. Nobody has a question on that? So we all understand it perfectly. So if I put it on a test tomorrow, we'd all be like, great. And I'd see 100% across the board. Good to know. Okay. So firstly, on Thursday, I am planning to give you your first assignment, which is where I will give you the Wikipedia data set, which I've partially curated for you. The data is still equally gross, but the data format is no longer as gross. What the Wikipedia data set is, in its raw form, are SQL dumps. And what these SQL dumps are, they're genuinely awful. Let's see. No, it's not here. Where did it go? No, never find. Oh, here it is. Okay. So we have the latest dumps, and there are a gazillion files here. What we really just want is the SQL files. So one interesting one is just page. And page is, has anyone seen a SQL data dump before? So what they are is instead of being like a smarter format that the SQL database can just directly import into itself, what it is instead is it's basically a SQL script. It's a script that, drops the database table if it exists, and then creates the database table with the schema, and then it's just a bunch of scripted import statements all the way down. And the reason that's so horrible is because um the reason that's so horrible is because whenever you're inserting data into this new table and it's scripted like this, it has to maintain the primary key index for every single insert that you do. And when you're doing a billion inserts, that's really slow. Like a perfect example is, let's see, because it's all in S3 now, thankfully. So you guys won't have to touch this. I got somebody suggesting that for the first project, I should show you the Wikipedia data set and have you import it into S3 yourselves and do all the stuff I did to do that. And I would say no, because I don't hate you that much. But I don't think I hate anybody that much. So these are the 5 tables that we're going to be using. This page links one is about 1.6 billion rows. So it's a good size table, and it tracks the links between Wikipedia pages. This thing took 3 days to import into MySQL. So I had to leave an AWS instance running for 3 days so that the stupid database import could finish, so I could actually do something with it. I was so angry by the end. It was so dumb. So Wikipedia is the perfect example of how to not publish a data set, because these SQL tables take so long to import. And it's not like this table is particularly large. It's only like 30 gigs of data when it's compressed, or when it's uncompressed, actually, which is not that big. But the reason it takes so long is because even though the amount of data is fairly small, the number of rows is, large. 1.6 billion rows ain't no joke. And so it has to keep track and maintain the indices for every single insert when it's doing this import, which is why it's so gross. Um, maybe, but the problem is we want the database integrity to be there, and I don't have that guarantee because there are some files from Wikipedia that actually fail to import because the dump is corrupted in some way. So I wanted to make sure that that wasn't happening. So you can, but and that's what the import does. It will disable the indexes during the import, except for the primary key. Because the primary key's data integrity has to be maintained. So that's the problem. So that was annoying. And the other thing is all of these four came from SQL imports. So the links between pages was a SQL import. So that's page links, and the page information was a SQL import, and the redirections between pages was a SQL import, and link target is related to page links, but it doesn't only include page links. This is another thing about Wikipedia's data set is that all of its information is just spread across a bunch of different tables, even though it probably shouldn't be. The exception to this is the the articles data, which is the actual text for the Wikipedia articles. This text comes from just a giant XML file that's 100 gigabytes that you have to download. So this 100 gigabyte file actually took maybe an hour and a half to convert from XML into a format that was actually compatible with Spark. So a 100 gigabyte file took an hour and a half, but a 30 gigabyte file took 3 days. Which goes to show you that the type of thing that you're doing with the data matters just as much as the amount of data and the type of data you're dealing with. So data type, analysis type, and volume. They all affect your performance. Questions on the Wikipedia dataset? Okay. We also have an example repo for CS535. And earlier today, I added this EMR tutorial that shows you instructions on how to start a cluster. So you don't have to look through an hour of lecture in order to find all these instructions. They're just written down for you here. So I did add a couple of things since the lecture, and I'll show you that right now. And we're just gonna create that. We went over the details of cluster creation already. The only thing I'm doing right now is I'm cloning an earlier cluster. That's the nice thing is that once you create a cluster in this class, you don't really have to do it again because you can just clone a cluster you previously created with all of the existing configurations. You just need one. Honestly, let's just do the same size. So whenever you start an EMR cluster, you need to pay attention to this on-demand price for each of the EC2 instances. So these kinds of costs can easily get out of control if you don't pay attention to, the size of the cluster you're spinning up and how long it's running. These clusters and, the method of interacting with Spark with these clusters, you must terminate the cluster manually. So even if it says, oh, I'm going to terminate myself after an hour of idle time, nothing you're doing counts as idle time. So it basically won't terminate. So you have to terminate yourself. And the scary thing here is that if you forget to terminate it and you leave it on for a week, then we're going to get a huge bill. And I don't want to have that conversation. So don't do that. One time, somebody from Equifax, who shall remain nameless, created an EMR cluster and in a different account from the one that we normally use. So we weren't checking anything and then left our team. And that EMR cluster was running for 4 solid months. And we wound up with a $35,000 AWS bill. So don't do that. Okay. We should be good. Okay. That'll take about 5 minutes to start up. So the stuff that I've added to the instructions is when you connect to the cluster, before you connect to the cluster, you need to look at the security group for the primary instance in your EMR cluster. And you need to make sure, and the security group contains configurations on what is allowed to connect to your cluster and the port numbers you're allowed to connect to your cluster over. And that affects, which applications you can use on your cluster. That's a big deal. So you'll find that if you're unable to reach your cluster for any reason, check your security group. That's the first thing I check is if somebody's trying to SSH into the cluster and it doesn't work, then check your security group. Actually, Trina came to me today because she started an EMR cluster at work and she was unable to, connect to the cluster. First thing I checked was the security group. And lo and behold, the ingress rule for allowing SSH traffic was not there. That's the first thing you should check if you can't connect to your EMR cluster. So what we need to do is you need to add ingress permissions for SSH, which is port 22 from every address. Yeah. Oh, yes. There we go. Okay. So has anyone seen a CIDR block before? Can somebody tell me what this means? Okay. So an IP address, what an IP address is, it's a 32-bit integer that is split into 4 8-bit parts. So, we can see these IP address numbers. I'll just look up what is my IP. So this is my public IP address. So if you want to talk to this laptop, you can reach out to this IP address and my laptop may or may not respond to it. All right. So what this is you'll see this first number. This is 1 byte. So what this is this is the first 8 bits of this 32-bit number, which is the IP address. Now, I forget what 132 is in binary. What is it? I think it's 1 0 0 0 0 0 0. Nope. Yeah. 128 plus 4. Yes. Let's check. I was wrong. It's that. Okay. Okay. So this is the first 8 bits of this address. The next 8 bits is 170 or 178, which is going to be 0B1. Help me out here. I can't math. 44. Actually, no, it needs to be 60, 76. Okay. So this is the second 8 bits, and it goes on and on and on. So what the CIDR block is it defines a range of where were we? Yeah, it defines a range of IP addresses. So what this means is when we say 0.0.0.0/0, what the slash represents is the length of the prefix that is fixed. So a CIDR block with this syntax represents a range of IP addresses. And so let's say we want every IP address that starts with 132.178. What the CIDR block would look like is 132.178.0.0/16. Now what the 16 means is the first 16 bits of the IP address are fixed. That represents the range of IP addresses that we're looking at. So this CIDR block contains every IP address that starts with these 16 bits. And everything that has any combination of bits after this is contained within this CIDR block. Make sense? Huh? So if it's all zeros and the CIDR block is 0, so if it looks like this, what that means is the prefix is 0. The prefix is 0 bits, and so if the prefix is 0 bits, that basically just means all IP addresses. The opposite of that is if you have a specific IP address and you only want to allow traffic from one specific IP address, the CIDR block, what does that look like? So yes, /32. So /32 means there are 32 bits possible in an IPv4 address. And what we're saying is we're specifying all 32 bits as part of the CIDR block. So it only allows traffic from this specific address. If we have a CIDR block that looks like this. Yeah, they'll probably be back to pick it up at some point. Yeah, we'll. Yeah. Okay, so the CIDR blocks make sense to everybody? All right. So what we're going to do right now is we're going to go to our security group and we're going to make sure that everything that we need to be allowed is allowed. So this is how we go into the security group. We need to look at the security group for the primary node. And this will tell us all of the inbound traffic that is allowed for us. So right now, we have port 22 that's already allowed on every IP address. So that's good. What we also need in addition to that is we need permissions for these 3 ports for our specific IP address. So I've added, this port, the other port, and the third port for a specific IP address, but this one is different because I was connecting to it, from a different place. So my IP address was different. So we need to change everything to match what my IP address is now. And oh man, what happened here? Oh, I think it's all just okay. Where did it go? Okay. So this is my IP address now. Okay. No problem. I'm missing one of them. I only changed 2 of them. Did I just change that one? I don't think I did. I did not. Okay, there we go. So those 3 should be all we need. Let's check everything. Sure. down. Okay. So now what we can do is we can actually connect. So this is a little bit different from the command that you can copy and paste with this link over here. So you can, connect to the primary node through SSH and it'll give you a command, but this command adds a few things. So the stuff that we need to add we need to add port forwarding for the Spark Connect server, which is what this is. And these two or these three collectively add port forwarding for the Hadoop UI and for the Spark UI. And this is so you can monitor your cluster and your Spark session to see what the progress is, and you can kill jobs with it and stuff like that. So these three things are for Hadoop and for Spark UI. So let's copy in here. Oh, yeah. Cluster. And this is the same as it's been for the previous examples. So now what we need is we need the public IP address of the primary node. And you can find that either just in here, because this is the IP address, but it has dashes in it, which is not syntactically correct. So you can also find this information over here. So the public IP address of the primary node is that, and we can just paste that in there. What we also need is we need the private IP address of the primary node, because for some reason EMR only makes the Spark UI directly accessible within AWS. For some reason, I don't know why they do this. So we're going to make it accessible outside AWS because it's not useful if it's only in AWS. Because my laptop does not belong to AWS. Oh, for this? Yes. Oops. Okay, we're good. Okay. So missing a little bit. All right. Okay. So we need the private IP address over there, and we need the private IP address over there. Do you want to connect to it? Okay. That's a very loud EMR logo. All right, so now we're in EMR. Everything's great. Just for reference, this is what it looks like when we don't have SSH ingress permissions for every address like we're supposed to. Here we go. Where is SSH? It is here. Inbound rule 7. Okay. Yep. So if I delete this rule, now we look at the rules. We do not have SSH permission anymore. So if we try to SSH into it again, then it's just going to hang because the server or the primary node is probably still receiving our request, or it might be receiving our request, but it's going to ignore us. So what this hanging means is we're not getting a response because somebody in AWS is ignoring our request. It's basically acting like we're not even there. Yeah, connection refused. There we go. So that's what it looks like when we don't have ingress permissions. So now we got to add them back in. Because the TCP. Let's do SSH. All right, there we go. And this should let us in again. There we go. Okay. All right. That makes sense to everybody? Good. All right. So now what we need to do is we need to start the Spark Connect server, which we did last time already. So we start the server and it gives us a giant log file to get a live feed from. Now, if you ever lose track of what exactly this file is for some reason, just know that it's pretty much always in this directory, /var/log/spark. And this directory is small, so it's easy to find. Wow, I wonder which one it is. So now we can get a live feed of that. Okay. So now what we need to do is let's actually, take a look at the Spark UI. So we can take a look at the Spark UI by first going to the Hadoop UI, and that's what this is. We've got a cute little elephant up here. Yay. So if we go over to applications, we can see our Spark Connect server. So we just click on that. And then we can see the tracking URL for the application master. So we click on that. And this is refusing to connect because, as you'll notice, this site that we're trying to reach is actually not directly accessible outside of AWS because this is the private DNS address of the primary node in EMR. So this is only accessible from EMR, this website. However, since we set up port forwarding, we can actually change this to localhost. And now it's accessible. We're in business. This is the Spark UI. Questions on that? Okay. So are there questions about the resources repo or anything else?
So related, probably really on interesting and see the other in the video class, I couldn't see the Shakespeare class.
Oh, you can see the same. Yeah. So I'm going to give you specific S3 paths for everything that you need to access because the buckets that aren't, I don't think the buckets owned by your account are going to be directly accessible to you. At least you won't be able to list them out. So I'm going to list specific paths for you to pull stuff from. You should still be able to pull stuff from it. If you can't, that's a big problem. Please come to me and talk to me about it. So if I give you a path for, all the data sets that we're going to use and you can't access it, I need to know as soon as possible so that I can get everybody permissions to access those things. Okay. We don't want a local session. Let's do an EMR session. Oh, and in the resources repo, there is also another, I gave out all the Spark examples that we went over for the past couple days. It's in the Spark SQL Python directory, and it's this file over here, Spark SQL example 3. And it goes through how to do the word count for the William Shakespeare data set. And it goes through all three methods that we did last time for counting the letter A for each line. Good? Good. Okay. So it goes through the functional programming method too, as well as the UDF and the original one with the explode. Okay, let's just restart this. Can I make this bigger? All right, now since I want to get stuff from S3, Sure. All right, we're in business. We have the data set. Now, what I'm going to show you this time is we're going to do some more functional programming examples. And we're going to go through different ways of how we can do things. So in this example, what I want to know is, here's our question. For each line in a Shakespeare play, I want to count the pairs of words that appear on a line together. So if and the appear on a line together, I want to know the total of how many times they appear on a line together in the entire data set. And that's for every single pair. Two for every line or for every pair of words. I want to know how often they occur in the same line. All right. So how do we go about doing this? We don't need to optimize it with functional programming first. We can just go through an obvious example. So that's going to be the with itself three times or once. It's just once per line.
Oh, so if there is a repeat on a line, it has to take.
There's a repeat.
Isn't that how many times you repeat? So if I were to count how many distinct words are on the line, new words are on the line, the difference is a repeat, and if there is a difference, then it would be a one with a line.
Yes. So then if we're going by that logic, then we should say that a word appearing twice doesn't actually link to itself. That makes it a little bit easier. So if the word the appears twice, then we would not count that as a pair at all. So we're going to exclude words that appear with themselves. We can do that. We can include them if you want. The solution will differ. We can do both versions. So let's say we want to know the unique time or the number of lines each pair of words appear. So if we're counting the number of lines each pair of words appear, then the uniqueness, doesn't matter. And if the pair appears multiple times on one line, it just counts as one. Because it's the number of lines that pair appears in. This is where, pedantics become very important, is how you ask the question really affects, what your answer is going to be. So that's a really good example of that. So if we go to, first, we're going to want to do the same kind of thing that we did last time, which is to split all the lines into words. But then things get a little bit tricky. Because now we have to decide, okay, how are we going to count the pairs? There are a couple ways we can do this. So firstly, we could, we can do the same thing we did last time, which is after we explode this so that we can strip everything off of the individual words, we kind of join them back together using the monotonically increasing ID technique that we discussed last time. So we can do with column, row ID, B, and that gives us a row ID. And so then if we want to join them back together and then kind of collect all the words into a new array, what do we do? We would do a group by row ID. And then we can aggregate. And then we can say collect set. Now collect set is a Spark aggregate function that will take all of the values in the column that you're aggregating on and produce an array of unique values. So the output from this function is we don't have any repeated values in this array. So it only collects unique values in an array column now for you. Word. And we're going to call this one unique words. Because now those words have no punctuation and they've been lowercase. And so now they've been sanitized in the way that we want. So let's see our progress so far. Took a second. That does not look like, that does not look accurate. What did we do wrong? Oh, I know what we did wrong. Someone else know what we did wrong? It's about where this monotonically increasing ID is. So let's remove this part. And let's just show what happens immediately after the monotonically increasing ID and what we do with it. So we generated the monotonically increasing ID right after we split the lines and exploded the words. So now in this data frame, before we add this monotonically increasing ID column, we have a data frame with only one word per row, right? And so after we have one word per row, then we gave every row a row ID. That's the wrong order we're supposed to do things in. What we were supposed to do is generate the row ID before we do the explode. So if we do that, then we should get something better. We also kind of removed the ID because we didn't select it. So that has to be in there too. Okay, so now we have a row ID and that looks a lot better. So now we have a row ID repeated with things that look like they would be on the same line, like by William Shakespeare. Makes sense to me? Good. We did another thing that was wrong, where instead of collecting the stripped words that don't have any, that are lowercase and don't have any of the punctuation, we aggregated the original words instead. So that stripping had no purpose. So that's what we needed to do. So let's see where that gets us. And we got it. So now we have another problem. is it looks like we still have the empty string. So we need to filter those out. Okay, let's try that again. Much better. Okay. So now that we've got everything in there. So now we need to generate different pairs of words. How are we going to do that? So we took out repeats, but now we want to generate pairs of words. No. So if two different words appear on the same line together, we want to know how often that happens. So Horatio and meat appear on the line together. So that would be a count of one. Yeah. Not necessarily, just on the same line.
So Horatio and me isn't there, and Horatio and Marcellus.
Yes. Horatio and meat is one pair in this expected data set. So this would be like an example row from the data frame for our answer to this question. And so let's try and find an example where we have two. We have just Horatio. Does it look like there are any examples in here of a pair occurring twice? Anyone find something? I don't see anything. But, another example would be exactly like Horatio and Marcellus. And would. And that would also have a count of one. And if Horatio and meat occurred in a different line somewhere else, also that count would be two, and so on. So we want to see how often these pairs occur throughout the entire data set. Does that make sense? Okay. So now we know what the problem is, because I didn't realize that was not communicated properly, is now we're about halfway there. So we got every row and the set of unique words that we have. So now we need to generate a bunch of pairs for all of these things. How can we do that? Mm-hmm.
But you need to, hang on, should you maybe stick them out? So they can, I mean, you're gonna do that, then you have to use the name up. If you do row-wise operators, it's gonna be, look through all the words in a row.
You can. So that's the functional programming solution. There's an easier solution with explode, but there are circumstances where you're going to want the functional programming solution. So the solution with explode is we could do dot select, and we select unique words. Let's do select expression. That's just easier. And we could do explode unique words. Okay. So what this gives us is, wait, we're going to see in a second. It's thinking. All right, there we go. So now we've paired up every individual word with the entire set. So then what we can do is we can say pair two. Pair two. And then we can do another select where we can explode the unique words again. Pair one. And then we'll keep pair two. And look at that. We have all of our pairs.
Look at that stuff.
Huh? Yes, and we can filter out things that are matched with themselves. We can say dot filter pair one is not equal to pair two. Or okay. So now we have all of our pairs. So now what do we do? Huh? Well, we
I'm trying to get a count of how many of these pairs there are on the same line. You should need the count. You need the line list for everything.
well, we don't need the line number. We just need to know how many times the pair occurs.
Not the line.
No, total.
Oh, how do you line for it?
Yeah. So we just need it in total.
So when you're going to have it, when you start, and so that you can divide in your count.
So we don't need to put them together and do a new struct because you can group by multiple columns at the same time if you want. There's another thing that we have to keep in mind. So actually, I'm just going to make the mistake, and then we can see how to fix it. We can group by multiple columns. And then we can aggregate over that. Just going to call it frequency. All right, let's see what we got here. Maybe I should have done this locally instead of on EMR. All right, so we see this pair occur, 122 times. So you and yourself occur in the same line 122 times. But the reverse might also be true. We might also get yourself and you, and that might be counted as a distinct pair. Let's see if that happens. Dot filter. See if that happens. I'm willing to bet that it does. Pair one in you yourself. So let's see what happens. Oh, wait. That's interesting. So what it's doing right now is it's counting every pair twice because this solution duplicates every pair. So because it duplicates every pair, what can we do to kind of stop that duplication? Yeah. Anyone have any ideas? Hmm? The unique function? Yeah, so how do we do that? So what we could do is because we know that we're generating two of each pair, right? Every time this explode runs, it's generating you yourself, and it's also generating yourself you. So what we can do is we can say the first item in the pair has to be greater than the second item in the pair. And this does two things at the same time. It eliminates the pairs of the word with itself, and it eliminates the pairs of the word with everything that's smaller than it. So it basically makes these pairs unidirectional. Hmm? So we can look at it again, and then we should only see one pair come out of this. There we go. So now we're not double counting. All right. That's one solution we can do, but I don't like this solution because it forces us to do an aggregation. It forces us to do this aggregation with the monotonically increasing ID. Now, there's a more efficient way to do it with functional programming, and this is a solution that Trina mentioned, which is we loop through all the stuff within a single row. Now, it's basically the same idea as the explode solution, but it does this within the row. So how would we do that? And it involves the same functions that we were calling last time. So it involves this transform function.
That the manager just realized so that on each board, what we're going to do is we are going to create, we want to go to each row and create our pairs so that we can create a count of the filling with pairs, just send this code and just send that. Oh, how do we do that? Because there still could be those number or those pairs in other data on the other one. So you can't just send an account. You're still going to have to send this pairs.
So we still do an aggregation, but it's only an aggregation. It's only the second one. We don't have to do the first one with monotonically increasing ID. So we still have to do an aggregation with this solution over here because it has to be a global aggregate over all the pairs for all the lines.
So for each row, we want to end up with the pairs.
Yes. So for each row, then we want to end up with a list of the pairs eventually.
And the function, you can do something. It's not what you're function from when you pass a function in here. And you're going to pass a function that's going to to recreate a new word beyond the control of the word, which will return the list of these buckets.
Are you talking about UDF?
Function two.
Well, so we also did that last time. So in this transform syntax, this is a function. Yes, so we can very easily write the function here. So we're going to do the same thing that we did last time, which is we're going to strip every word in the same way that we did last time. And um, the way that stripping works is, well, okay. And that's just because I don't feel like writing it again. Okay. So what this does is it will take everything that's not a letter character and replace it with the empty string. So this is just like the regular expression replace up here, except for the fact that instead of doing it per word and every word is a row, you are looping through the entire words array and you're applying it per element of the array. So that's what transform does. So we can see what this looks like. It's yes. Looping equals slower?
Yeah.
Well, so you still have to deal with the same amount of data at the end of the day, but it's more about how you're dealing with it. Because in this solution, what we're doing is we're taking the existing rows, or we're taking the existing array, we're expanding it, and we're also making a copy of the monotonically increasing ID for every word row. And we still have the same number of words that we have to, strip everything out of and then aggregate over. And then we have to collapse it back again when we're done doing the stripping. So it makes this more efficient.
That's been done. Are we having this to the data? Caching data in the parent.
Yes. So Spark might be doing some optimization where it like knows that monotonically increasing ID is going to be unique per core and per partition. So it might do some crazy optimization, but I don't know if it will. Honestly, that might be an interesting question. We can actually look at the plan and see. So if we were to execute this again, actually, let's just store it in memory dot persist. So we can do a persistence. We'll talk about storage level some other time. Let's keep that and see how it goes. And then we can go to the Spark UI. And does it not have a interesting? It must have already computed it and still had it in memory. So if we look at storage, we should see that one in there, and we do. So there's 200 partitions and all of it's cached in memory, and this is how big it is. And this is an extremely ugly name for the pair counts. Okay. So if we go and look at the job, And Spark might also be optimizing this because there's only one machine. These are all the stages in here. See, scrolling sideways. I don't. Um, Not necessarily. This is an. It could be object hash aggregating. Let's look at an earlier job because all of these were skipped. Object hash aggregate, that was skipped too. That's too far. It's not even the same one. Okay. Whoa. Talk about ugly. Jeez. Okay. So this object dash aggregate, I'm willing to bet that that refers to no, but that could be either. That could be either the group by aggregate on the pairs or the monotonically increasing on B. Does it say which ones? We could also look at actually, let's just save this part. Because if we just save that, then that'll get us where we need to go. Let's see if this actually does an aggregate. So we can look at the most recent job. Huh? Yeah, it's skipping these stages because we've already executed them a bunch of times, and so it has the results of these stages cached already. So that's why they're being skipped right now. It's because it's a redundant computation. So over here, it definitely looks like there's some data exchange happening. So if we look at the stages, we can see shuffle read. Yep, maybe. Look at the stage. Shuffle read size. The problem here is that we're looking at the results of cached computations. Honestly, what we're going to do either next time or next week is we can look at the differences between these kinds of computations on the Wikipedia data set, because then that will be much more noticeable on a larger data set. Because right now, since everything's cached and we don't have time to restart anything, um, the computations are still instant. So we'll look at it next time. All right. So if we wanted to do all this row-wise, so now we have everything stripped, then what do we do? So first we need to do the same thing that we did up here and make sure that the list of words is unique. And so we want to make sure that we're not repeating words in this new words column. So then we could say with column, words. And then forget what the actual thing is. Array distinct, that's what it's called, is a collection function that removes duplicate values from the array. So we can do that. Huh? So we're going to so this new words column is an array. We know that because this is what the transform function returns an array. So we can say that expression, array distinct, new words. Okay, so now we have all the unique words in there. So now we need to generate the pairs. So we can do something very similar to what we did with explode, which is we can kind of do a first explode to pair every word with the entire array, and then we can do a second explode to pair the word with every element of the array. Does that make sense? So it's going to be something like with column. So we're going to have to do, what should I call this? This is going to be weird. We're going to call them pre-pairs. And what this is going to look like is we're going to have a transform. And we're going to transform the unique words array with a lambda expression. And that's, we're going to create a struct. And we're going to have x as pair 1. And then unique words as pair 2. This is getting a little bit long. Okay. There we go. All right. So that's one of our steps. And we can see the intermediate step when we, whoa. Okay. So right now, what this looks like, and I do realize that this is rather gross to look at, but what this looks like is we generated the words. Actually, we didn't lowercase them, which is what we should do. So let's add a lowercase to this. Try that again. Okay, that's better. Okay, good. Everything else is good. Okay. So now we've generated this pre-pairs, which pairs every word with the entire array. And this is very similar to what we did with the explode solution. And so now what we do is we kind of have to do an inner transform. So with column, what do we have to call this? Word pairs. And this will be dot expression. So let's say transform pre-pairs. And then every pair, we're going to transform into an array. So we're also going to have to transform the inner array. X dot pairs 2. And we're going to do struct X dot pair 1 as pair 1. This is also getting a little long. And that's pair 1. Y as pair 2. Okay, let's see if that works. So now we have word pairs where, oh, we're missing some, what are we missing? Oh, that's what we're missing, extra parentheses. Okay. Oh no, what happened? Oh, okay. It's pairs. Okay. So now what we have is now we have a bunch of pairs. We have by and by. We have by with William, by with Shakespeare, and then we have William with by, William with William, and William with Shakespeare. And then we have Shakespeare with by, Shakespeare with William, and Shakespeare with Shakespeare. So that's what we want so far. The next step is, huh? The what with the array?
So if I have one array
Okay.
with all of the words,
Okay.
and since I'm passing the function, then I want to stuff that is, I can do the for loop, whatever we can do, that says like first with the second and third with the third and fourth and fifth, fourth, fifth, and then on the turn. And you're saying how many each of those things, so, yeah.
That's exactly what we're doing here. So what you just
You want to try to get all of those.
yeah, so what you just described is exactly what we're doing here in functional programming form. So what we're doing is we're basically doing like a double for loop over the same array. So for the first element of the array, we loop over every other element of the array and we generate a pair. And we do that for every element of the array. So this is a double for loop.
Yes, I just. Like a column, really the array, the array.
Oh, this is just the intermediate steps. This is just to show the intermediate steps. So we could have all of this as one giant expression if we wanted to.
Oh, okay.
So I'm only illustrating the intermediate steps when we go through all this. So then what we need to do is, this is actually an array of arrays, right? So this is a double nested array. So there's one array, there's another array in here, and there's another array in here. There's three arrays in here, and we want one. So what we're going to do is we're going to flatten the whole thing like this. And what that gives us is a totally flattened array, which is what we want. And so then our last step is to take the transformed array and generate our unique word pairs. Because in this example, we have words paired with themselves, and we also have repeated word pairs. So we have by William, and then we have William by, which is not what we want. So we have to do the same kind of filtering that we did above, which is unique word pairs. Sure. Yeah, we'll just do. filter word pairs. X dot pair one is greater than X dot pair two. All right. Now let's see, we got here. Oh, I forgot to write the parentheses again. All right, that is much closer to what we want. So we have William by, William Shakespeare, Shakespeare by, and that's basically all we want. So now that we have those pairs, we can do an explode. Explode unique word pairs as pair. Then we could do a group by, and since it's a struct, we only need to group by the single thing. Ag count star. There we go. And so then we can look at the other example we saw before, which is yourself and you. Which one appeared first? I can't remember. So yourself that appeared first or you? I think it's you that appeared first. So filter pair equals struct of you with self. Is that a type error? I have incompatible types. Oh, they have to have the same type name, or they have to have the same column names. Is it the opposite? Oh, it's the opposite. Oh, that is also a problem. There we go, 122. So that gives us the exact same count. So this is the functional programming example where we did basically everything row-wise until we couldn't. So this is how you could do everything row-wise without a UDF and without another aggregation over the monotonically increasing ID. So this is slightly more complicated, but this is also how you program in functional languages. Like this is normal in a functional programming language. And this is how it would look. I realize we're a few minutes over time. Are there any questions? All right, we're done.
These words in the way I'm following. Okay. Words come, right?